Okay, let's talk about adders a little bit. So we'd like to make some machines that add numbers together. And we've already discussed why you might need to take a different approach than just a truth table. For example, if you had a 64-bit adder, adding two 64-bit numbers together would have 128 inputs. So your truth table would have 2 to the 128th rows. So if you did a brute force approach, you'd have 2 to the 128th rows that you'd have to process. So that would take you, I don't know, 2 to the 40th or 10 to the, so it's about 10 to the 40th rows. So if you process them at 1 billion rows a second, you're still looking at 10 to the 30th seconds, even for a computer to process this, which is older than the age of the universe. So the brute force approach is no good. So we need to kind of think through how to build an adder from other components. So, and that's what we're going to build to in this lecture here. So first, let's understand how you may think of adding. So you might start over here in the ones place and add these digits together and get a 6. And then you would add these digits together, which now we're in the tens column, and we'd get 14. And since it was 90 plus 50, it's really 140, but we would just write the 4 and then carry the 1 over into the hundreds place. And now we add all 3 of those digits. So that would be an 8 and a 4, which is a 12, carry a 1, and we get a 6. Now let's do the same thing in base 2 over here. So we'll look at the ones place first, and there's no carry coming in. Like, I'm always going to have a 0 there to start. So that's going to be a 1, and then I carry nothing because I just have a plain old 1. So a 0 plus a 0 is a 0, carry nothing. A 1 plus a 0 is a 1, carry nothing. A 0 plus a 1 is a 1, carry nothing. A 1 plus a 1 is a 2. But I can't write a 2 there. I can't have a 2 in base 2. So the way I represent a 2 in base 2 is a 0 and a 1. Remember the 1, 0, this would be equivalent to a 2. So I've carried a 1. That gives me now a 3. I represent a 3 as a 1 carry a 1 because a 1, 1 is a 3. And a 1 plus a 1 is a 2. And then I get a 3 again. So the procedure for adding in base 2 or any base is the same as what you would do in base 10. I add up the columns and I carry over into the next column information as needed. Okay? So I'd like to build a machine that adds up just one column here. And I want it to work for every column. So I'm going to call this a column adder. The column adder can have, if you look at how many inputs is it going to have, it's got a number from, or a digit from number A. It's got a digit from number B. Those are these ones here and here. And it also could potentially have a carry in. So that's this digit right here. This is the carry in from the previous column. So I'm going to add in another input called carry in. So we've got 3 inputs, and now let's see how many outputs does it have. Well, it's going to result in this digit right here. That's an output. And it also could result in that digit, which is the carry out. And since I have a carry out, I probably should call this carry in. Hence the CIN label there. So this column adder has two outputs, the regular output digit and the carry into the next column. We can build this column adder by making a truth table. So 0 plus 0 plus 0 would give us 0, 0. 0 plus 0 plus 1 would give us a 1. Same with a 0 plus a 1 plus a 0. A 1 plus a 1 gives us a 2. A 1 plus a 0 plus a 0 gives us a 1. A 1 plus a 0 plus a 1 gives us a 2. A 1 plus a 1 plus a 0 gives us a 2. And finally, a 1 plus a 1 plus a 1 gives us a 3. And then from here, we can make K-maps and draw circuits and get what we need for that column adder. That you should be able to do. Okay, what I'd like to do next, though, is show how we can use these individual column adders to connect them together to make an adding machine that can add two 5-bit numbers, two 3-bit numbers, two 50-bit numbers together. So for each column, I need this column adder machine. So each column needs one of these machines. The carry in for the very first column is going to be a 0. The output of the first column, I'll put in a different color. I'll put it in yellow. Here's the output of the first column. Here's the carry out for the first column. And then here's the column adder for the second column. Here's the output of the second column. Here's the carry out of the second column. And then here's the adder for the third column. So each column needs its own column adder. So we can maybe see how this is going to work. So let me, on the next page, let's draw a big box which represents our adder overall. And let's make a 4-bit adder. So this will be a 4-bit adder, which means it takes in two 4-bit numbers. So we'll say this is number A and this is number B. And these are the less significant digits. These are the more significant digits. It's going to have 5 outputs, a number, plus maybe a carry out. Or if you want to think of that carry out as just a number, fine. You could also think of this as the most significant bit here. And then this over here would be the least significant bit for the output. Okay, so I need a column adder to do the first column. And I'm just going to draw it like on its side here. So we've got A, B, and carry in. So here's our value. I'll take the, oops. Like that. And our first carry in, we could either take it as an input or I could just make it 0, which I could ground it there. We have two outputs, the output and the carry out. The output will go to the first output of the answer, and the carry out will go into the carry in of the next column. And because the next column is going to get the second bit of B, the second bit of A, and its answer is going to go in the second column of the output, and its carry is going to go into the third column over here. Finally, the last one, its output is going to go to the last output, and its carry out will just connect to there. So I haven't filled in the rest of the details here, but this is the gist of a 4-bit adder. You should be able to go through and connect the rest of these wires and see where they go.